Hi there and welcome to chemistry. My name is Jeremy Krug, and in this series of videos we're learning about heat and energy in chemical reactions and in physical processes as well. If you're new to my channel, welcome. I'd like to invite you to look around, take a look at the playlists. That's where the action is. This is the place for all things honors chemistry and AP chemistry. So if you like what you see, please consider smashing that thumbs up button. I would really appreciate it. And if you don't want to miss a thing, make sure that you subscribe to my channel and become a part of the community. Now, as we talk about heat and energy, let's take a look at a very typical chemical reaction that might take place in a laboratory. Here we have hydrogen gas that's reacting with chlorine gas, and that forms two molecules of HCl, hydrogen chloride gas. Now, sometimes we just take for granted that if you mix these two substances, they're going to react and create the product. But the fact is, in order for molecules to react, those molecules have to collide with each other in a certain way. They have to satisfy two requirements. They have to collide with, first of all, sufficient energy. So that means that when they collide, they can't just have perhaps a glancing blow or collide with very little energy. They have to collide with enough energy so that they're actually going to do something. Now notice the second requirement is they have to collide in the correct orientation. So what does that mean? Well, it's kind of like this. If we have these two molecules here, they have to collide in the proper orientation. Perhaps that is the wrong orientation, the wrong direction. But this might be the proper orientation. This is kind of like taking a key and putting it into a door or into a lock. You know that the key can only be inserted into the lock in a very specific direction or specific orientation. If you put the key into the lock in the wrong direction or backwards or upside down, it's probably not going to work. And so that is a requirement for these molecules. They have to collide in just the right orientation so that they're going to fit together. Another example of this would be Legos. Perhaps you've played with Legos before, and you know that in order to put the two Legos together, you have to stick them together in the right direction. If you take two Legos and take the two raised sides and try to stick them together, it's just not going to work. You have to put them together in the right direction. Now, if you satisfy those two requirements, the molecules collide with enough energy and in the right orientation, then the molecules are going to fuse together. And so here we have our two molecules. We have an H2 molecule and we have a Cl2 molecule, and they have fused together. And they have formed what we sometimes call an activated complex. Now, an activated complex is just an unstable, high-energy transition state molecule. This is not the reactant, this is not the product, this is something that's kind of in the middle. This is a very temporary molecule that's formed after the reactant state, but before the product state. And as you look at this molecule, and you might give this a formula of H2Cl2, but you can see that this is not very stable. At this point in the course, you've probably learned that hydrogen has one valence electron, and so it can't really make two bonds, can it? Likewise, chlorine has 7 valence electrons. It's trying to get the octet. It really doesn't have room to make two bonds like we see here. So this is not going to last very long. The fact is that 2 of those 4 bonds are going to have to break. Now, if the 2 bonds that break are this bond right here and this bond right here, then we're back to square one, aren't we? We basically have our reactants again. But what if the bonds that break are this bond right here and this bond right here? Well, if that's the case, well, now we have 2 molecules of HCl, just like this. And so now we have produced our products. See, this is how molecules collide. This is how molecules react with each other in order to create products. This is sometimes what we call collision theory, this idea that molecules have to collide with enough energy and in a certain orientation so that they'll create that activated complex, that transition state, and then different bonds will break in order to make the products. Now, if that happens, we're going to have our products. Now let's take a look at the energy of this reaction as time progresses. So I'm going to make a little plot here, and on the x-axis I'm going to put time. So as the reaction progresses over time, we're going to go farther to the right. And then the energy of the molecules will be plotted on the y-axis. And so the higher up we are, the more energy we have. The farther down we are, the lower or the less energy we have. And so as we can see here, the reactants start with a certain amount of energy, and then as the reaction gets started, the reaction energy goes up and up and up and up and up, and it hits a peak, and then it starts going down and down and down and down and down. In fact, it goes lower than where we started, and then it levels off and it stops changing. So here we have what's sometimes called a reaction energy profile. So this is just a profile or a diagram or a graph, if you will, that shows how the energy is changing as the reaction proceeds. Now, there are some very important parts of this profile that you need to know about. So this amount of energy that we have labeled A right here is called the energy of reactants. Hopefully that makes sense, because reactants are what you have at the beginning or before a reaction actually gets going. And so the energy of the reactants will basically be a plot from the very bottom of the graph up to the starting point. So that's our energy of reactants. Now this energy quantity over here that I have labeled B, this is called energy of products. And hopefully that makes sense as well, because products are what you have at the end of the reaction. And this is, of course, at the end after things have essentially concluded. So this is the distance from the very bottom of the plot up to the ending point of that reaction. That's our energy of products. Now this peak right here in the middle that we have labeled C, that's a very high energy. That's called the energy of activated complex. If you think about how we defined activated complex a few minutes ago, hopefully this value makes sense, because we said that the activated complex exists after the reactant state, but before the product state. Well, that's what we have here. Activated complex is in the middle. It's after reactants, but before products. It's also high energy and unstable. In fact, activated complex is the highest energy quantity on this plot that we could look at. It goes from the very bottom up to the very tip top of that peak there. And it's unstable because it only exists at this very small point at the very top of that curve. So that's our activated complex. Now there are a couple of other important points on here that you need to be aware of. And the next one is what I have labeled D. So it's the distance from the starting point of the reaction up to the peak. And that's called the activation energy. Now, you've probably heard the phrase activation energy before. This essentially refers to the energy that's required to start a reaction. Now, you know that we sometimes have reactions that take place that require a certain amount of activation energy to get started. For example, think about baking a cake. If you take all the ingredients and put those together in the batter and mix it up and just leave that batter out on the counter, you're not going to have a cake, are you? You have to add energy, you have to add heat in order to make that batter react and turn into a cake. And so the heat from the oven provides that activation energy. Or lighting a match. If you have a match, you know that it just doesn't spontaneously start burning. You have to strike it against the little pad there on the side of the matchbook. Well, there's an activation energy that you have to apply in order to get that reaction to get started. Well, the same thing here. The activation energy is how much energy it takes to get a reaction going. Now, in chemistry, we like to abbreviate this as E sub A. So if you ever see an E sub A in perhaps on a test or a quiz or a homework problem, that refers to the activation energy, or the energy of activation as we sometimes call it. Now, the last part of this plot that I want you to be aware of is the distance between the starting point and the ending point. So it's basically the net change that's taking place over the course of the reaction. And I have this labeled as E, and that is called the change in enthalpy. Change in enthalpy. Now, we abbreviate this as delta H. Now, H, enthalpy, is a certain type of heat. Now, you have to be careful here because enthalpy and heat are not exactly the same thing. Enthalpy is a very specific type of heat. For example, if you take your hands and you start rubbing them together like this, you start to feel some heat generated. Well, that heat is friction. That's not enthalpy. Enthalpy is the heat that is associated with the breaking or the forming of chemical bonds. And so enthalpy is associated with chemical bonding. And so when reactions take place, enthalpy can be released, it can be absorbed. In fact, it actually tells us if a reaction is going to be exothermic or endothermic. Now, if you take a look at this plot right here, we can see that we start out with a certain amount of energy, and then over the course of the reaction, we have a net loss of energy. So that means that we released energy into the surroundings. This is called an exothermic process. We have an exothermic reaction. Most reactions tend to be exothermic, as it turns out. On the other hand, if we had started the plot at this point and then we had ended it up higher, maybe like up here, well, that means that the reaction would have gained energy, and that would have been an endothermic process. In exothermic processes, if you stick your hand next to it, your hand is going to feel hot because heat is being released. In an endothermic process, you stick your hand next to it and your hand is going to feel cold because heat is being absorbed from the surroundings into the system. So exothermic and endothermic processes. So be aware of the different parts of this reaction energy profile. Now, the next part of this video has to do with reaction rates. Now, very often in the chemistry laboratory or in industry as well, we're interested in how fast reactions go. And sometimes we want a reaction to go as quickly as possible. Under other circumstances, we want to slow down a reaction and make that reaction go much more slowly. Let's think about 4 ways that we can affect or change the rate of a reaction. The first way is to add a catalyst. Now, you've probably heard this word before. A catalyst speeds up a reaction. But the neat thing about a catalyst is it's not consumed. It does not get used up over the course of a reaction. And the way this works is that it lowers the activation energy of a reaction. This actually gives us an alternate pathway for the reaction. So if we were to back up to that reaction energy profile, if we were to add a catalyst here, well, it would lower the activation energy to the point that maybe this hump, or this hill, I should say, would go to maybe this point here. It wouldn't go as high. And so we'd have a lower activation energy, and the reaction would go faster. So a catalyst is a good way to speed up a reaction. Now, a second way to speed up a reaction is to increase the temperature. Now, the reason this works is that when you have faster moving molecules, it causes those molecules to collide more frequently and with more force. And we talked about earlier in this video how chemical reactions take place when molecules collide. And they have to have enough force when they collide. Well, when you speed up the molecules, all of a sudden molecules are moving faster. You're going to have more frequent collisions, and you'll have more forceful collisions. And that's going to result in more effective collisions that actually result in a chemical reaction being carried out. I think at some level, most of us understand that increasing the temperature causes an increase in the rate of a process. For example, if you were to bake a pizza and you put that pizza in the oven at a very low temperature, you know that it's going to take a long time to cook the pizza. If you raise the temperature of the oven, it's going to cause that pizza to cook much more quickly. If you go to New York City, where they may bake that pizza in a coal-fired oven at close to 1,000 degrees Fahrenheit, they'll be able to cook that pizza in 4 minutes. So the higher the temperature, the faster the rate, and the less time it takes to cook the pizza. And this works with pretty much any chemical reaction as well. So adding a catalyst is our first way. Increasing the temperature is a second way. A third way to speed up a reaction is to increase the concentration of the reactants. I think at some level we understand this as well. If you ever have a dilute acid spill on your fingers, like, let's say orange juice, that's not going to burn you, is it? Or if it does, it's going to take a long time for that to happen. On the other hand, if you're in the laboratory and you spill a beaker of concentrated hydrochloric acid on your fingers, well, you're going to have to get that washed off of your hands as quickly as possible. The higher the concentration, the faster something is going to react. And the reason this works is that when you have a higher concentration, the particles of the solute are smashed closer to each other in the solution, so they're able to collide more often. In a dilute solution, the solute molecules are farther apart, and so they don't collide quite as often. So the reaction takes place at a lower rate. So increasing the concentration is a good way to speed up a reaction. How about the fourth way? The fourth way to speed up a reaction is to decrease the size of the particles. And if you've ever tried to speed up a reaction using solid particles, you've probably done this. You may take larger particles and use a mortar and a pestle or some other instrument to grind it up into smaller pieces or smaller particle size. Now, the reason this works is that when you have smaller particle size, the material has a greater surface area. And when there's more surface area, there are literally more places or more spots where a chemical reaction can occur. In chemistry, we call these active sites, literally spots or places where a reaction can take place. So if you want to speed up a reaction, you can increase the surface area, grind it down into smaller particle size. So these are the four ways to speed up a reaction: adding a catalyst, increasing the temperature, increasing the concentration, and decreasing the particle size. Now, as you know, sometimes we actually want to slow down a chemical reaction. For example, how about the reaction of food spoilage? That's a reaction that takes place very quickly under certain circumstances. But if you want to slow down the rate of food spoilage, what do? Well, you probably put that food into a refrigerator, don't you? And that's because when you lower the temperature, you lower the rate at which food spoils. So we actually apply these four ways of changing reaction rate in our everyday life. Hey, hope you learned something about chemical reactions and reaction rate and how chemical reactions take place as well and the energy associated with them. If you learned something from my video, please slam that thumbs up button. I would really appreciate it. And please consider subscribing as well, because when you subscribe, that means you won't miss a thing. And that also helps recommend my videos to other like-minded chemistry students that also want to learn chemistry just like you. Hey, thanks for watching. I'll see you in my next video where we can learn some more chemistry together.